तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, today's class we shall discuss the realization of semiconductor memories. We have already seen in the last class the block diagram of a memory chip. You have the decoder X, we have the buffer here, X buffer, then X decoder and driver, and which is followed by the memory array, cell array, okay, and here you have the Y buffer, then Y decoder driver, and the sense amplifier, you have the control circuits, okay, and you have the output buffer, so we have seen that if you have, say for example 2 to the power n memory cells, you are going to have n address lines, okay. This is of course assuming that the memory is configured as 1 bit memory, okay. That is, if you have say 1k into 1 bit memory, you have 1k is 2 to the power 10. So, you have 10 address lines in order to select the memory, and that is the 10 address lines are divided into 5 address lines going to the X buffer and 5 address lines going to the Y buffer, okay. So, this one may be A is 0 to 5 and this one may be A 6 to 10, okay, and this goes to the decoders. At the output of the decoders, you have, if you have n input lines, you have 2 to the power n output lines, all right. So, here again you have 2 to the power n address output lines. So, here you have an array, okay. So, you have the output of the decoder, X decoder, okay, you have 2 to the power n lines this way, and you have again a number of columns. So, you have number of rows and number of columns, and at the intersection of the rows and columns you have the memory cells, okay. So, basically what you do is this X address decoder selects one of the rows, that is one of the rows is selected, one row goes high, okay, and then at each column has the information corresponding to that particular row, okay, the cells located at that particular row, okay. And then what we do is the sense amplifier, you have a number of sense amplifiers, okay, the number of sense amplifiers is equal to the number of columns, okay, and then finally this decoder driver, okay, selects the Y decoder driver selects one sense amplifier, okay, and at the output you have the output corresponding to the particular sense amplifier which is selected, all right. So, basically you are selecting one row with the help of the X decoder driver, and you are selecting one column with the help of the Y decoder driver, and basically you are selecting the cell at the intersection of that particular row and that particular column, okay. So, if you have, again as an example, if you have 1k into 1 bit memory, you require 10 address lines, so 5 the X, 5 and Y, and you have 32 rows and 32 columns, 2 to the power 5 and 2 to the power 5, okay, and okay. So, you are selecting one particular cell here. Now, of course, if you have 1k into 16 bit memory, say, So you will have 16K cells, all right. So you have 2 to the power 10 into 2 to the power 4 cells, okay. So you basically have 16 such memory chips in parallel, okay. You will have as many so you will have many number of 16 number of times the sense amplifiers, okay, and you will have 16 output buffers, all right. So basically if you have so many of them side by side, you will have 16 times the number of columns, all right. So it is going to be a wide memory, all right. So now if you want to make it a square memory, okay, usually you want to make the array a square array, okay, you remove 2 address lines here and put it in the X buffer, all right. So you have how many? 7 address lines here, 3 address lines here, you say, okay, and then you have you are selecting, and basically you have 16 of them, okay. So 2 to the power 3 into 2 to the power 4. So you have 2 to the power 7 columns, okay, and here you have 7 of them, so you have 2 to the power 7 rows. So you can make it a square memory, all right. So this is about the memory organization, okay. Now you can have different types of memories depending on the type of cell which you have, okay, the way you are storing the information, okay. So memories as such, semiconductor memories, okay, can be basically classified, I should say, into 2 types. One is volatile and the other is non-volatile, okay. Volatile means the memory information is lost if the power supply is not there, okay. You require the power supply for retaining the memory. Non-volatile is even without any power supply, the memory is retained, okay. So examples of this is the ROMs, okay, the different types of ROMs, okay, which actually do not require any power supply to retain the whatever is stored, okay. It is inherently stored there. We shall come to that. Here in the volatile you have the RAMs, okay, and this RAMs again can be classified into the static RAM and the dynamic RAM, okay. Again this name, they are different because in the mechanism of storage of information. In a static RAM, okay, the information is going to be retained, okay, as long as the power supply is there, okay. But in a dynamic RAM, okay, the mechanism of storage is is by charging a capacitance, okay. But what happens is if you keep the if after some time the capacitance gets discharged, okay, because there are leakage paths and the charge may get may flow out through the leakage paths, and the whatever is stored in the memory may be lost. So you have to do periodic refreshing of memory, okay. So that is a dynamic RAM, okay. So we shall study all these different types of memories, okay, look at how their cells look like and how the memory, how you can do the major operations, that is reading from a memory as well as writing into a memory cell, all right. So first we shall take up the static RAM, all right, and see the different types of static RAMs which you can have, okay. Just like we have seen different logic families, okay, that is basically the same logic can be realized using different types of circuits, okay. You have seen bipolar logic families, MOS logic families. Similarly for static RAM also you can have different types of static RAMs, for example bipolar static RAMs, MOS static RAMs, CMOS static RAM, okay, bi-CMOS static RAM, okay. So you have the different types, okay, and of course the circuitry is different. So we shall go through that, okay, and similarly for the other memories, all right. Basically for all these memories the architecture or the organization is like this, is similar, okay. These are all what are, in fact all these memories are what are called random access memories, okay, all right, in the sense that the random access memory is such that the access time for each memory location irrespective of the memory location is the same. Okay, that is, if you want to access any memory location, whether it is here or here or here, okay, does not matter, the access time is going to be the same. This is as opposed to the sequential access memory, all right, where you have to access in a sequence. Okay. For example, you know, for example, a practical example is for a tape record, cassette tape, for example. If you have different some things stored in that cassette tape, okay, depending on where you are located now, okay, if you want to locate another memory location, okay, the access time is going to be different for different locations. All right. So here this is all random access, that is, the access times are the same irrespective of which memory location you want to access. Okay. Of course, you also have semiconductor sequential access memories, okay, but they are not much in use. Okay. So we will not actually discuss them. All right. So the static RAM cell consists of two inverters basically, okay, connected back to back. So this is what is used to store information in a static RAM. All right. So two inverters. So if this, here you have logic 1, okay, this is an inverter, so here you have logic 0, okay, this is fed back, okay, so this is a perfectly stable configuration. All right. So once you have anything here, you know, this will be retained as long as the power supply is available for these inverters. All right. Now suppose you change this to 0, this will automatically change to 1, and again this is a perfectly stable configuration. All right. So this is the basic structure of a static RAM cell. Okay, two inverters connected back to back. All right. Now what you have is, in order to access these cell, you have two switches which is connected like this, okay, and these switches are actually activated by this word line, okay, by this word line. All right. So when this, I should say, all right, when this line is high, okay, you can say that this switch goes to the closed configuration, okay, and when this output, this line is low, the switches are open, okay, and this end is connected to the bit line. So this line is called the word line, okay, and these lines are called the bit lines. So one line is called a bit and the other line is called the bit bar. Okay. So this word line is the output of the X decoder. All right. This word line is the output of the X decoder. So you have such cells, okay. So if this is the cell, this is the cell, okay, memory cell. So what you have is, this is the word line, say so many word lines, okay, and with each word line you have the bit and bit bar lines, and you have cell connected like this, okay, sorry, the cell connected here, okay. So this is a bit and bit bar line, okay. This corresponds to one column. So here you have another cell, all right. So here you will have another cell, okay, and similarly you will have cells connected everywhere, okay. So this is a word line, okay. There are 3 word lines shown here, okay, and there are 3 columns shown here, okay. So depending on which word line is high, Okay. So, depending on which word line is high. So, for example, if this word line is high, okay, all the cells connected on this particular row will be connected to the bit and bit bar lines. Okay. In all the other rows, okay, the cells will be disconnected from the bit and bit bar lines. So, in this column, if this particular row is high, you have information corresponding to this particular cell. Okay. That is again going back to this. So, if this particular row is high, the information on this what is stored here, okay, is available on the bit and bit bar lines because this switch is closed. All right. So, this information has now, if you want to read the cell, okay, you have to have some mechanism to interpret whatever is stored in this particular cell. Okay. If you want to write into a cell, okay, basically again you select that particular row, okay, and then that particular column, one particular column you have to energize, okay, and you must be able to force, okay, one end this point, okay, if you want to change from 1 to 0, you must make this point go to ground, okay, all right, force it to ground, okay, so that this point becomes 0. So, automatically this goes to 1, all right, and like so you force a particular value into that cell, all right. So, that is how you can read and write into a particular cell. Okay. So, this is in general. Okay. Now, we shall look at specifically different types of static RAM memories. Okay. Firstly, we shall take up the bipolar static RAM. Okay. So, the bipolar static RAM cell looks something like this. So, again you have the word line. Okay. So, you have actually two lines like this, W plus. So, here the cell is something like this. Have the bit and this goes here. So, you can recognize the bipolar inverter here. Okay. So, you have two inverters, bipolar inverters. Okay. So, this is a current source here, this is going to minus VEEC. So, basically this bipolar memory is like an ECL memory, it is okay, ECL cell. Okay. What you have is, you have you can look at, if you see this, okay, you have this is a inverter, bipolar inverter, okay, that is a transistor with a resistance in the collector side, and so this is going to be the collector output is going to be the inverted form of the base input, okay, and this collector output is connected to the base of this transistor. Okay. So, if you consider this as an inverter, okay, a bipolar inverter something like this, okay. So, this is the input, this is the output, all right. So, the output of this is fed as input here, okay, and the output of this is, the first inverter is fed as input to the second inverter. Okay, just like the cell which we had discussed, okay, two inverters connected back to back, the output of one inverter is connected as the input to the other. Okay. The other thing is, this inverter, this transistor is a multi emitter transistor, it has two emitters, okay, also this one, okay, and the other emitter is connected to this emitter is connected to the bit line, and this say is connected to the bit bar line. all right. So, you have the word line here, okay. You have this cell here, and here you have the this is an emitter coupled structure, okay. You can see here both the emitters are shorted, and this goes to a current source just like in a ECL, okay. This goes to a current source which goes to a power supply, negative power supply, okay. So, this is the bipolar cell. So, in fact, you are going to have similar cells, okay, like this, okay, and this is all of them are connected like this, okay. This is corresponds to one row, okay. In this row you have large number of cells like this, okay. Similarly, okay, on this column, okay, you are going to have other cells, okay, all right, and they of course there are different word lines, okay, to energize these different cells in this particular column, all right. So, this is one particular cell. Now, let us see how this memory works, okay. Now, you have for a memory you basically have three states, okay, you can say, or three conditions. One is the holding state, okay, where you just retain whatever is stored in the memory, okay. The same information is retained, okay. Basically, you are not reading or writing, all right. You are just holding whatever is in the memory, okay. In this case, what is done is, in the holding state, okay, this W plus line, okay, goes low, okay, and the bit and bit bar lines are both high. All right. Okay, that is in the holding state. Now, of course, if which automatically means that if you are basically it means that when you are not selecting a particular cell, okay, for reading or writing purpose, okay, the W plus should go low, B should be low, and bit bar lines should both be high, okay. Obviously, it means that if you are selecting for reading or writing purposes, okay, the state, it has to be in a different condition. We will come to that, what is going to be for W plus and bit bar lines. So, basically what happens is, if the W plus goes low, okay, now this here what you have is a current source, all right. So, the voltage in this line, so which is actually called the W minus line, that is which is the common emitter point here. The W minus line is the common emitter point here. So, what happens is, if the W plus line goes up, okay, this W minus potential is also going to go up, or the if the W plus potential goes down, W minus potential goes down. So, this is a current source, okay. So, basically the voltage at this point can be anything, it does not matter, okay, all right. All right. So, now what happens is, here you see you have two cross coupled inverters, okay. Now, usually what is going to happen is, one of these transistors is going to be on and the other is going to be off, okay. So, suppose this T1 and T2, T1 is on, okay, and T2 is off, all right. So, T1 is on means what is going to happen is, there is going to be a collector current flowing, okay, and if there is a collector current flowing, okay, this base voltage at the voltage at the base of T2 is going to be W plus, what is the voltage at W plus minus the drop across this resistance, okay. So, this is off, and since this is off, okay, there is no current flowing across this resistance. So, the base voltage of T1 is going to be the voltage at W1, okay, and since the emitters are constant, emitter voltages are constant, okay. Now, obviously, so the difference in the base emitter voltages of T1 and T2 is going to be the drop across this resistance, whatever is the IR drop across this resistance, okay, all right. So, obviously say suppose you are you have 0.3 volts drop. See here this Schottky diode actually limits the drop across this resistance. So, this drop when this is conducting fully is going to be around 0.3 volts. So, the base emitter voltage of T2 is going to be 0.3 volts less than the base emitter voltage of T1. And since when T1 is conducting, say the voltage is say 0.8 volts, okay, VBE of T1 is 0.8 volts. So, VBE of T2 is going to be around 0.5 volts. Okay. So, obviously when VBE is 0.5 volts, it is below the cut in voltage. So, this is going to be off. So, the collector current is going to be 0. So, there is no drop across this. Okay. So, here you have the voltage between W plus and W minus, okay, if you take this path, you know, is going to be basically equal to VBE of T1, all right. So, okay, this is true when T1 is conducting. If T2 is conducting, you will have a similar argument. You can show that T1 is going to be off, all right, and again the difference between W1 and W plus and W minus is the base emitter drop of T2, okay, which is around 0.8 volts. So, what happens is this is constant. Okay. Now, if you raise W plus voltage, okay, W minus is also going to follow, okay, with a difference of 0.8 volts. Okay. And since this is a current source, okay, even the voltage, if the voltage across the current source changes, it does not make any difference. An ideal current source, okay, the current is going to be independent of the voltage drop across it. So, okay, so the same current is flowing. Okay, this current which is flowing depends on the current which is flowing through this transistor. All right. So, okay, so basically if W plus is increased, W minus follows, it goes up. W plus is reduced, W minus follows, it goes down. Okay. So, now in this condition, if you make W plus low, all right, W minus is also low. You are raising the bit and the bit bar lines. This voltage is made high, bit and bit bar both are made high. So, what is happening? This emitter voltage is going to be low, okay, whereas this so if you consider the two emitters of this transistor, any transistor T1 or T2, okay, the emitter, this emitter, okay, which is called the holding emitter, which is all right, which is connected to W minus, which is called the holding emitter, that voltage is going to be much less compared to the emitter voltage of this other emitter, which is called the bit line emitter. Okay. All right, you have made this voltage high, you have made W minus low. All right. So, if you consider any of these transistors T1 and T2, okay, what is going to happen is, since the this emitter point, okay, the emitter voltage of the holding emitter, okay, is less than the bit line emitter, okay, it is the holding emitter which is going to conduct, and the bit line emitter, okay, is not going to conduct. It is not going to be the voltage across the bit line emitter base emitter junction is going to be much low, is going to be much less, okay, and that is going to be off. Okay. So, basically there is no current which is going to flow along the bit and bit bar lines. All right. So, in the holding state, okay, what happens is you reduce W plus, which means that you reduce W minus also, okay, and you are reducing the voltage of the holding emitter, and you are raising the voltage of the bit line emitter. So, the base emitter drop across the holding base emitter junction is going to be much higher than that of the bit line base emitter junction. So, this is going to conduct, all right, and the other bit line base emitter junction does not conduct, all right. So, that is the holding state. Okay. Now, suppose you want to reading state, say, that is you want to read the state of the memory, okay, whether a 1 or 0 has been stored. You have to follow a convention, that is, suppose you say that when T1 is on, what you have stored is a 1, okay. If T2 is on, what you have stored is a 0, okay. You can have these two conditions. When T1 is on, obviously T2 is off, and when T2 is on, obviously T1 is off. Okay. Now, you want to read the state. Basically, you want to see which of these transistors is on. Okay. Then what you do is, basically you have to transfer control from the holding emitters to the bit line emitters, all right. So, what you do is, you make W plus high and bit bar lines low. Okay. All right. So, basically what you are doing is, one of the rows, okay, one of the W plus line goes high, okay, one of the W plus line goes high, and one of the bit and bit bar columns is going to go low. Okay. In all other rows, okay, so at the intersection of that row and column, only in one cell, okay, the word line is high and the bit and bit bar lines are low. Okay. In the other cells, okay, you do not have this particular condition. Okay. Now, what happens is, if you are making the word line high, okay, you are raising this, if you are making W plus high, you are also raising W minus potential, again because this drop, you know, is almost equal to VBE of a transistor, the difference between W plus and W minus. So, when this goes up, this is also going to pull it along, the potential. Okay. So, this emitter point voltage goes up, the bit and bit bar lines potential goes down. So, what happens? So, suppose T2 was on, okay, that means the base voltage of T2 we have seen was around 0.3 volts greater than the base voltage of T1. Okay. All right. So, this emitter, the emitter of T2 connected to the bit line is going to conduct, okay, whereas T1 is not going to conduct. So, basically the control is transferred from the holding emitters to the bit line emitters. Okay. So, you are going to get a differential current flowing in the two bit lines. All right. One of the emitters is going to conduct, one of the bit lines is going to conduct, current is going to flow, okay, and the other current is not going to flow. All right. So, this difference can be sensed by a sense amplifier. All right. We shall come to that. In fact, we shall discuss the sense amplifier when we take up BiCMOS memories, okay, basically because in BiCMOS also you use bipolar sensing. All right. So, that is going to be similar. Here what you are doing is, you are going to sense the difference in the two currents, the currents flowing in the two bit lines. Okay. So, if T2 is on, this line is going to current is going to flow in this line, whereas in the other line there is no current flowing, and of course, if T1 was on, it is going to be different. All right. Okay. So, reading state W plus goes high and bit bar lines go high. All right. Now, writing state, again what you do is, W plus goes high, all right, and one of the bit lines is going to go low. Okay. So, either bit or bit bar lines go low. Okay. All right. In all other columns, okay, the bit lines are high. All right. So, in all other columns the bit lines are high, means that the transfer is still with the holding emitters. Okay. In one particular column, so you in one particular row the W plus line goes high, and in one particular column one of the bit lines goes low. All right. So, what is happening is, by raising the W minus line, you are basically transferring control to the bit line emitters, okay, and you are reducing the potential in one bit line one particular bit line. So, what you are doing is you are since you reduce the potential there, so that base emitter junction, okay, the voltage is going to be much more. VBE of that transistor is going to be much more because the emitter voltage is reduced, is forcefully reduced. Okay. So, that transistor will turn on. So, if that transistor turns on, there will be a collector current flowing, okay, and if that collector current is flowing, so it is going to reduce, it is going to turn off the other transistor. Okay. Also because the bit line, okay, or the emitter voltage is going to be made much high on the other transistor. Okay. So, that other transistor, the VBE is going to be pretty low, okay, and so it is going to be turned off. All right. So, by doing this, okay, we can write information into a particular cell. That is, depending on which line is made low, we can either make T1 go conduct or we can make T2 conduct. All right. So, this is how a bipolar static RAM cell works. Okay. So, again as you can see, this particular cell, okay, functions by adjusting the voltages, okay, on the bit and bit bar lines. Okay. That is, by adjusting the word line voltages and the bit and bit bar line voltages, you are selecting a particular cell. Okay. You do not have special switches actually to select that particular cell. Okay. Now, for this bipolar memory, okay, the advantages are, of course, that it is going to be quite high speed, okay, that is always there. The reason is, okay, that for this cell to operate, okay, the voltage swings on the bit lines, okay, are quite low, okay. Compared to a say CMOS type of memory, okay, the bit line voltages have the swing on the bit line voltages, you require much larger swings, okay, to be able to sense that. Okay. Here basically you are sensing the current which is flowing, all right, which is flowing here. So, the bit and bit bar line voltages, okay, they need not vary much, okay, you are just sensing the current. Okay. So, the potentials on this line, okay, is not varying by much. Okay. In fact, this may the voltage variations on each of these lines for the entire different operations, okay, must will be within 1 volt or so, less than 1 volt. Okay. You do not require to go beyond that, because the VBE of a bipolar transistor is just 0.8 volts. Okay. To switch on and switch off a bipolar transistor, okay, you require a very small voltage variation. Okay. So, that is why you don't require, you require less time, okay, to sense the whatever is stored in that particular cell. Also, because the current on these lines is being driven by bipolar transistors, okay, and because of the large current drive capability of bipolar transistors, okay, this is going to be much faster. All right. The bit lines are driven by bipolar transistors. Okay. So, that is another. So, that is for this reasons, okay, this memory cell or this type of bipolar static RAM is going to be faster compared to MOS type memories. But there is a basic disadvantage here. The disadvantage is that it is very difficult to make large size memories. Okay. The reason is like this. Say in the holding state, see if you are selecting a particular cell, okay, all the other cells, okay, I mean are in the holding state. Okay. In fact, even if you are selecting a cell, there is going to be a current which is flowing, all right, and this current, say suppose a transistor is in the holding state, a cell is in the holding state, okay, it has been found that you require at least of the order of a few microamperes of current to flow through the transistors to keep it on. Okay. So, suppose T1 is on, okay, at least a few microamperes of current must be flowing through through this transistor to retain it in the on condition, okay, because you have to switch the other one off also, all right. So, there is say if you say that the holding current for a particular cell is say 2 microamperes, okay, all right, and if you have say if you think of a 1 megabit memory, okay, it actually requires 2 amperes of current flowing through this memory, okay, just all right, flowing through the cells, okay, which is a very large amount of current, all right. So, you see that it is very difficult because of the large power dissipation problem, okay, to have large size ECL type memories like this, okay. So, the advantage is of course higher speed, but the disadvantage is you cannot go for very large size memories, okay, as you can in the case of say MOS type of memories, because the static power dissipation is very much less, all right. So, that is the basic disadvantage. Another disadvantage with this is that the control signals, okay, that is for reading, writing and holding operation, they are much more complicated here, right, compared to the CMOS memories, okay, MOS and type of memories, all right. Here you have to generate the signals, okay, and they have to be very much precise, okay, because the variation in voltages are very small, you know, from one state to the other, okay. So, you have to have very the control signals, okay, must be generated are much more complicated, okay, the generation of these control signals when you compare with MOS type of memories, okay. So, this is the comparison of the bipolar type memories with CMOS memories. So, obviously nowadays the trend is to have large memory the memory chips having a large density, okay, large sizes, okay. So, for that reason one has to go to for MOS type of memories, okay, because also the density we can achieve in MOS type of memories is much larger, primarily because the power dissipation is going to be much less, because you do not have this static power dissipation, okay. As also MOS transistors, you know, can be occupy much less area compared to bipolar transistors, okay. And so, say suppose you have a 1 megabit memory, you actually have 1 million such cells, okay. You must realize that you have 1 million such cells. So, the major portion of the memory chip is taken up by the cell array, all right. And so, if the cell size can be reduced, okay, then you can have a smaller area, all right. So, that is another constraint, okay. So, MOS type memories are more suited for larger density memories, okay, whereas bipolar is not very much suited for that. But of course, if you want a small memory but very high speed memory, okay, for example, the cache memory in the computers, okay, you have a small density memory, but which you want very high speed, because the computer is going to interact with that memory much more regularly than the other memories, okay. So, you can have that made of bipolar memories, okay. Okay, so shall now just talk about the MOS memory cell, okay. Again, the MOS memory cell has the similar structure, the same structure as we have seen, okay, the two inverters connected back to back, okay. Now, this can be NMOS, okay, that is NMOS inverter. You have say a depletion mode NMOS, okay. So, this is a depletion mode transistor, okay. So, in that case this is an inverter structure, the two inverters. So, the output of this inverter is connected to the input here, and the output of this inverter is connected to the input here. So, this is the cell, okay, and then you have pass transistors which act as switches, okay, to connect them to the bit lines. So this is a word line, okay, this is a word line. So this is on this row you will have a large number of such similar cells, okay. So this is on this row, and on this column also you will have a large number of such cells. Okay, so this is a cell, okay. Now this cell is going to be selected when this particular word line goes high, okay, that is the X decoder output goes high for this. So these two transistors turn on, and this particular cell is connected to the bit lines. So since only one word line can be high at a time, so in each column, okay, only one cell is connected to the bit lines. So you have information corresponding to that on the bit lines. And then of course, with the help of a Y decoder, you choose one particular column, okay, and that is the output which you get, okay. So then you basically choosing one particular cell, because you have already chosen one particular row, and now with the help of the Y decoder you choose the output of one particular column. So here again, this is an inverter. So if the input of an inverter is high, all right, the output is going to be low, and so the if you have 1 here, okay, which is the output of this particular inverter, so this input is high, so the output is going to be low, and so like this. So this is a perfect stable configuration. But of course the NMOS the problem is of static power dissipation. So almost all MOS memories nowadays use CMOS, okay, because in a CMOS inverter you know that the static power dissipation is not there. So because almost all the you see most of the memory cells they are not changing state for most of the time, all right. So there is no power dissipation as such. There is power dissipation only when there is a change of state of the memory cells only. So otherwise there is no power dissipation as such in the cells, okay. So this is an inverter. The output of this inverter is fed as input here, okay. So the output of this inverter is fed as input here, output of this goes on as input here, the other inverter. So there are two inverters, and the output of one goes as input to the other. So this is a memory cell, CMOS memory cell, okay, and we can select again the particular cell in the same way, okay, by making one word line go high, and then selecting one of the different columns, okay. So here we an information is stored by making one of the inverter output, when one of the inverter output goes high and the other is output is low. So you can say that if this is the bit line and this is the bit bar line, when this is 1, the 1 is stored, okay, when here it is 0, a 0 is stored, okay. And again we can force this memory cell to go to a particular state by forcing some certain voltages on the bit and bit bar lines, okay, and so controlling the state of this particular cell. That is basically the writing operation, all right, and while reading we just read the information what is stored in that particular cell, okay. Now in the next class we shall take up again some aspects of design of this CMOS memory, and then we shall see how you can have you can combine the advantages of both bipolar static RAM and a CMOS static RAM in a bi-CMOS static RAM, okay, which combines the advantages of the CMOS static RAM of being a low power dissipation memory, okay, all right. So you can have high density of memory. At the same time, you get the advantages of bipolar, that is a high speed memory. So if you want high density as well as high speed, okay, you can BiCMOS can be used, okay, which from where you derive the advantages of the two types of memories.